So our first talk today is going to be from Lorenzo, who's going to tell us about detector R&D, I think specifically within the European context, but maybe more generally as well. So yes, you can take it away.
Yes, exactly. I've been asked to give a broad overview of the detector R&D with the focus on the framework in which the R&D is developed at CERN in Europe with the DRD collaborations. Okay, so why, of course, we are talking in this conference about the physics at the highest energy with colliders. It is obvious that this is possible if adequate detectors will exist. So for having the experiments at the next collider machines, it is necessary an intense R&D activity for producing cutting-edge detector technologies. So the R&D is mainly driven by the physics goals, but also collider conditions are important, beam-induced backgrounds, radiation, etc. So the overview of this talk is really broad. I will talk basically about everything. I won't go specifically in precise topics, just to give you an idea on how the work is organized in Europe through the DRD collaborations. So most of the material of this presentation is taken from the talks presented at the Open Symposium in Venice for the European Strategy for Particle Physics updates. So you will find the credits of the people that gave the updates at that conference. Okay, let's talk about the timeline for developing a large detector for a collider. In our experience, we know that the typical development cycle is between 20 and 30 years. We can take as an example the phase 2 upgrades of Atlas and CMS for the high luminosity LAC. Basically, the first ideas started in at the beginning of 2000 years with the technical design reports between 2017 and 2021. And basically, the production started recently. The commissioning will end in 2030 when the data taking of the Illumi LAC will start. Of course, this is for large-scale experiments, while for smaller-scale experiments, obviously the development cycle is shorter. But now in this talk, I will focus on big experiments. So what will be the next generation of detectors? So here, as next generation, I refer to the detectors that will be deployed after the upgrades of Atlas and CMS. We expect, or at least they are proposed, the discussion, their approval is ongoing. An upgrade for ELIS, ELIS 3, a second upgrade for LCB, LCB upgrade 2, the upgrade of Bell 2, and also the EPIC experiment at the Electron Ion Collider. So if we stay with the future Illumi LAC detectors, these are supposed to start in round 5, that is around 2035, 10 years from now. In fact, if we considering the development cycles, we are basically approaching the technical design report phase. So the technical design report of ALICE 3, LCB upgrade 2, and also of EPIC is expected in around 2026. So these are under study since several years, almost 10 years. Then after these detectors, the next generation we expect is the generation of the X electroweak and top factories. Here you have a few examples of detectors proposed for E+ E- colliders, the idea detector for FCC EE, the click detector for the click, the linear collider, the detector for CPC. So these detectors are expected in late 40s and 50s of this century, so if we consider this 20-30 years cycle, the time for the R&D is now. So we cannot wait for developing the R&D for these detectors if we want them ready, let's say around between 15 and 25 years from now. What will happen beyond the E plus E minus colliders? You know, we have discussed about this in the past days. We expect probably a muon collider and also the hadron collider, the FCCHH. So for the muon collider, there are already 2 detector proposals. If we consider the technically limited timeline proposed by the International Muon Collider Collaboration, a muon collider is expected in the 50s. The FCCHH detector could be expected optimistically in 2070s. So if we stay with these timelines, the muon collider detector should come before the FCCHH. But the FCCHH detector is a very complex detector. You will see in the next talk. So we have time to work on this, but the first ideas and concepts should be developed in these years, in the next years. Otherwise, we won't have 30 years to develop all the necessary technologies. And if, muon collider will come in the 2050s, again, we have to reach mature concepts in few years from now. So let's talk about the requirements, because the requirements are so first we think about the requirements and then we design a detector. So physics requirements, they depend on the physics program. For X factories, we need an outstanding momentum and impact parameter resolution. And we would like to separate the hadronic decays of W, Z, and X bosons to have the necessary precision to fulfill the program of the X factories. For precision electroweak and QCD physics, of course, we need an excellent detector with good resolutions, but we would like also to have an outstanding absolute and relative accuracy on the luminosity, because we want to measure cross sections, basically. For heavy flavor physics, we need an excellent impact parameter and secondary vertex resolution, but also an excellent Icala energy resolution for the reconstruction of B-hadron or C-hadron decays in neutral particles, and also a good particle identification. While for searches for new physics, like feebly interacting particles, we need an excellent sensitivity to detached vertices, up to meters if we consider long-lived particles, hermetic detectors, and precision timing. So these are the physics goals, but we will talk, I will talk also about the backgrounds and the radiation requirements later. Okay, so now let's keep the LUMI LSC detector phase of the LSCB upgrade to true and LIS3. Let's go directly to FCC-EE. So how we can meet the requirements on the several physics for the several physics programs. Today we have 5 detector concepts. 2 of them are ILD and CLD, are basically evolutions from the detector concepts of click and ILC, but of course, I mean, in A plus E minus colliders, from the point of view of the environment, is pretty. It's not the same, of course, but these detectors can be easily adapted to FCC-EE. So how what is our program to meet the requirements for the physics? You see, for the vertexing, we want silicon maps, so monolithic devices. This is true for all the 5 detectors. While for the other systems, there are different proposals. As an example, for the tracking, we have silicon, time projection chambers, gaseous detectors. For the PID, there is also a ring imaging sharing of option. For the calorimetry, we go from silicon, scintillator, to full silicon, to do a readout, noble liquids. And also for the immune system, we are thinking on scintillators and gaseous detectors. Even the magnitude of the magnet for the spectrometer is different. So there are several things that are going to be developed as R&D. Of course, we have also the freedom to combine the technologies later, but this is what is being studied now for the FCCEE. Now, if we go beyond the plus, let's take a quick look at the Muon Collider FCC-HH requirements. So these are the physics requirements for the Muon Collider. Basically, we want, I don't go through the table, but just to say that the performance we want for the Muon Collider is between the LUMI-LAC and the E+ and minus colliders. In fact, the Muon Collider is a lepton collider, but so for precision physics, but we have the beam-induced background. It is also a discovery machine, so we want to go to the higher energy possible, also with the measurement of the particles, and we care about precision, but not so much. So let's say that the performance are in the middle between ILUMI and the E+ and minus colliders. And also radiation levels are similar to the ILUMI LAC. So it's clear that there is a synergy of the Muon Collider detectors development with the ILUMI LAC and the FCC detector R&D. Just to say that the technology R&D will go in the same directions for these free collider proposals. I mean, the proposals, it will happen, but we should take profit of these directions that are followed in these days. The FCC-HH is a bit more complex because we'll have a flux of particles 10 times more than ILUMI-LAC. The ionizing dose will be more than 20 times higher than the ILUMI-LAC. So these extreme conditions will require groundbreaking technologies that they don't exist now, but I mean, we have more years at this point. So which are now we have talked about the future machines, the detector proposals, but which are the general R&D directions for each subsystem? Let me check the time so I can. Okay. Okay, let's start from the vertexing. In this table, do we have the comparison of the performance of several proposed detectors, detectors for FCCE. Well, these are more requirements, let's say, that are met by the technologies proposed. So the FCCE, EPIC, the Alice-free upgrade for the track and the vertex system, and this is the current inner tracking system for Alice. We have seen before, for the vertexing, we will need monolithic active pixel sensors called MAPS, basically for all the future experiments, because they are the main candidates for meeting this excellent performance. On the single point resolution for FCCEE, we will need the 3 micrometers compared to 2.5 or the vertex detector of Alice-free that will come much before. Alice-free will need 100 here it is nanoseconds, that's probably it is picoseconds, while FCCE will arrive to 20. So yes, basically this is the key technology for the vertexing, where the integration of sensitive elements and logic elements are on a single chip. We can take profit of the industry for the standard CMOS processes, but this should be modified for particle physics. For the tracking and muon detection, the key requirements are the resolution on the momentum around 0.1% at 45 GeV, a good particle identification. In gaseous detectors with the D over the X or the N over the X, we want a pi K on separation up to 100 GeV. And then we are working on the 4D tracking. For this, we need a resolution of the position of 30 micrometers and a time resolution below 30 picoseconds. So this is basically the goal of the tracking devices, having a resolution in the order, time resolution in the order of 30 picoseconds. This is true basically for all the detector proposed, for ILUMI and for FCC-EE. So the key technologies here are gaseous detectors, from wire chambers, drift chambers, time projection chambers, Bricker pattern detectors, but also silicon detectors, and also scintillating thin fiber detectors. So there are several options to meet these requirements for the tracking systems. For the calorimeters, the key requirements are an energy resolution around 3-4% at 100 GeV, and also the compensation on the response of electrons and hadrons. They should be suited for modern algorithms that we have developed in these years for the calorimeters, from the particle flows to machine learning-based approach. In fact, the design and R&D for the calorimeters now is done thinking on these reconstruction algorithms. We talk as an example of particle flow calorimetry. And then we have this new concept of 5D calorimetry, where the calorimeter sensors measure the energy, the position, so 3 dimensions, and also the time. Even here, there are many options to achieve these requirements, from sandwich calorimeters to optical calorimeters, noble liquids with high granularity, but also the dual readout calorimeters that measure scintillation and Cherenkov effects at the same time. And of course, for the optical calorimeters, we need also efficient photon detectors. In fact, for the photon detection, that is necessary not only for the calorimeter, but also for the particle identification, as in ring emerging Cherenkov detectors. The key requirements are high quantum efficiency, high speed, low dark rate, radiation hardness, and also the stabilization with the temperature and in a cryogenic environment. Here, the key technologies are what we already know, the silicon photomultipliers and the traditional PMTs that are going to several developments. And if we go to the particle identification, the key requirements is a pion photon and hadron separation over several momentum ranges. This can be achieved with ring emerging Cherenkov detectors and time of flight detectors that use, as an example, they can use ultra-fast silicon detectors like LGADs and similar detectors. Not only the subsystem for measuring the particle properties, but also the trigger and data acquisition is something we should develop because it's you know that is fundamental for our experiments. Here the requirements will be an high rate data transmissions, also using photonics. There are new trends like triggerless and streaming readout. These are being developed also considering intelligent backend processing with machine learning, and also heterogeneous trigger farms, CPU, GPU, and FPGA. I've put the scheme of the LCB RAM-free trigger system, the current trigger system that is the first triggerless system that uses both GPU, CPU, and we are also testing FPGA. I say we because I work in the SMB collaboration, sorry. But there are several challenges. So we have to maintain these heterogeneous frameworks that it is not a simple task. And also we should avoid the bottlenecks between the ASIC and the DAQ. The electronics is another transversal topic for the detector development. The requirements are dedicated chips, so the ASICs, and also the programmable logic with FPGAs. The new developments are related to these intelligent front ends based on machine learning techniques. There are several challenges. The first is the special requirements compared to industry that leads to an high cost, and also the increasing gap to industry state of the art. This is a problem that should be solved. Otherwise, the costs of our electronics will grow. We have talked about this yesterday. Will grow. Then there are also emerging technologies, and I put here also the artificial intelligence. So the quantum sensing, we discussed about this yesterday, so I don't go into the details. These are mainly, the quantum sensing is mainly driven by the non-accelerator particle physics experiments, dark matter searches, axion and neutrinos, but there are some ideas for colliders like the chromatic calorimeters and the nanowires. Then related to the software and artificial intelligence, we can consider it an emerging technology, but nowadays we use it everywhere. But we expect a tighter integration of hardware and full software stack, and an integration of the real-time AI in front-end and trigger. And also the detector optimization with the AI, in the sense that the design of the detectors can be performed with AI techniques, basically maximizing the performance of the other figures of merits, and there are several studies on this already. So these are the main directions we are following all over the world with for the development of the future experiments at accelerators. But what is the framework in which this R&D will be developed in Europe, and in particular at CERN? So everything started in 2020 for the European Strategy of Particle Physics update of the 2020, where the recommendation was that the community should define a global detector R&D roadmap and support proposals at the European and national levels. So the ECFA committee prepared this roadmap in 2020 map with these 200 pages documents, where they defined 9 different tracks for with several different topics for the development of the detectors. We arrived at the 2022 with the roadmap implementation plans. The effect of this was basically the approval and then the starting of these collaborations that are called DRD, Detectors R&D Collaborations. So we have 8 different DRD collaborations. They have different histories. In fact, we have 3 of them that are based on previous R&D collaborations, DRD1, the gaseous detectors, the semiconductor detectors, DRD3, and DRD6, the calorimetry. As an example, calorimetry was based on the previous CALIS collaboration. In fact, if you check the number of institutes and the number of people participating to these 3 DRDs, you have more than 700 people and more than or around 150 institutions. So these are well-established collaborations that they reinvented themselves with this DRD framework. Then there are completely new collaborations: DRD2, liquid detectors; DRD4, photodetectors and PID; DRD5, quantum sensors and emerging technologies. Then there are 2 DRD collaborations that are transversal activities: electronics and mechanics and integration. So these are approved for an initial period of 3 years, and then will be reviewed. There is an annual review by this DRDC committee, and then will be extended. They are organized in working groups and work packages. The users can be registered at CERN because the DRD collaborations are registered at the CERN Greybook. So the participants to the collaborations are CERN users, can be CERN users, and certain DRD collaborations asked for a fixed yearly membership fee, targeting common projects. However, you should consider that DRDs are not funding proposals, so the resource request has to be signed by the funding agencies, okay? This is an ongoing process in the funding agencies, like in the INFN here in Italy. In INFN, the review of the fundings for detector R&D is strictly connected with the activities of the DRD. So we should motivate in which DRD collaboration the R&D we want to develop is connected, and then there is a discussion on the fundings. So, but what is the goal of these DRD collaborations? If we consider the readiness scale, the usual one that is used in this kind of researches, if you consider that the readiness level from 1 to 3 is the blue sky R&D, then from 4 to 6 we go from the technology development to the technology demonstration, and from 7 to 9 from the system development to the actual deployment of the system. Basically, the goal of the DRD collaborations is bringing from the level 3 to the level 6. So from the feasibility to the final technology demonstration, okay? So basically, the technology R&D inside the DRD will lead to mature concepts of the detector we are developing, while the engineering phase will be another thing, not inside the DRD. At that point, a different funding system will be required, and again, it will go to the funding agencies. Okay, this is the framework. I should also say that this has been also inspired by the CPAD framework in the US that came before the DRD framework. Now, how much time I have? Okay, let's go into the highlights from the DRD activities. Of course, it's impossible for me to show everything, so in an arbitrary way, I decided to show a few highlights of the several DRDs. So let's start from DRD1, the gaseous detectors. A mention should go for sure to the drift chamber of the IDEA detector for the FCC. The interesting thing of this system is that it features 340,000 wires in total. That is an enormous amount of wires. And this is a huge mechanical problem. And this problem is faced with a mechanically accurate simulation that has been prepared and performed. Then we have the straw tracker proposal for the inner tracker of the FCC EE. You see here an image of the structure of this inner tracker with gaseous straw detectors, and again, they have prepared these simulations with several scenarios, and they are looking at the resolution, the transverse momentum as a function of the transverse momentum for these different scenarios. Another interesting proposal developed in the DRD1 is the picosec detector that uses micromegas. This has been proposed for several systems. As an example, it has been proposed for the muon system of the muon collider detector. So these devices are fast, and they can provide a time resolution around 100 picoseconds. Then, again, in the DRD1, they are developing this time projection chamber for the ALICE upgrade and the ILC, and basically they have demonstrated with simulation that the the D over the X resolution below 5%, that is the target of this kind of device, is possible basically with all the considered technologies, GEM, GridPix, and Micromegos. So this is a common development for ELIS and ILC, since we were talking about synergies. Then the RD2, the liquid detectors. This is, as I said before, this is a brand new collaboration. In fact, in these detectors, there are several challenges from how to manage the charge, the reading of the charge or the light, depending on the type of signal you have. Then there are studies on the target properties of the liquid itself. And then the scalability of these detectors, because they have a very large mass, large area readouts, so the scalability is not a trivial thing. Let's say that the state of the art of the liquid detectors is driven by neutrino experiments, dark matter experiments. In fact, you have Dune, Xenon, dark side inside this collaboration. But it is important also for collider experiments. As an example, for calorimeters with liquid noble gas. This is an example. In fact, if we go to the DRD, first there is the DRD3 with semiconductor detectors. We have talked already about this in this talk. So the main research topics is the development of the CMOS monolithic active pixel sensors, the maps, but also the low gain avalanche detectors, LGAD, for having an excellent timing performance of 25 picoseconds and for achieving the requirements for the 4D tracking. And also these sensors are developed with having in mind an extreme radiation hardness. Okay. So there are several types of these devices, from the AC LGAD to the trench isolated LGADs, inverse LGADs. There is a huge work done by several institutes. Here I have an example of TimeSpot. There is a project in INFN for developing a pixel with an excellent time resolution around 20 picoseconds. ELIS is basically the detector that nowadays has most has a great experience on developing these devices. There are also other interesting projects like the Arcadia project, the advanced readout CMOS architectures with the pleated integrated and sensor arrays. It is considered for the ELIS-free time-of-flight system. It is supposed to achieve a time resolution of 20 picoseconds, but is also considered for the idea detector, okay? Again, synergies between the next generation detector at the high luminosity LHC and the future detectors at X factories like FCC. So calorimeters, the DRD6. So the main drivers for the development of the calorimetry are the X factories, in particular FCC EE. If we want a good resolution, equal resolution for measuring the X to gamma gamma, we would like to have 20% over square root of E plus 1%. For heavy flavor physics, we need even better, like 3% over square root of E. Here you have basically the separation between the W and Z bosons mass. That is the goal of the FCC EE detectors in the hadronic decays for several hypotheses of resolution on the invariant mass peak. And you see, we should achieve for having a good separation, let's say between the red and the black curves, between 1% and 3%, let's say. So it is really an excellent resolution that could be achieved with the 5-dimensional calorimeter paradigm that is considered now in the development of the calorimeters. So energy with an high energy resolutions that by reducing the fluctuations by construction of the calorimeter, with improved algorithms like particle flow and machine learning approaches, the position with high granularity, and also the timing with fast timing information. So there are several, really a lot of ideas on calorimeters, from the sandwich calorimeters with alternating layers of active and passive layers. We go from solid states with silicon, again, maps detectors, sensors, to optical calorimeter with scintillation tiles or strips, with gaseous calorimeters with RPC and multi-pattern gaseous detectors. But as I said before, also the liquefied noble gas calorimeters that this is already a successful development in particle physics, as an example, the Atlas calorimeter. For the optical calorimeters, we have, again, a lot of ideas from a homogeneous calorimeter, ECAL, electromagnetic calorimeters, like Krillin, that we have talked about it yesterday or 2 days ago, no, I don't remember, that is an homogeneous calorimeter taught for the muon collider. Sampling electromagnetic calorimeters like SPACAL, the spaghetti calorimeter, that is studied for the LSCB upgrade 2, and here you have also a photo of the fibers, the spaghetti inside the tungsten, I think in this case. But then also sampling hadronic calorimeter, like the dual readout calorimeter that is being developed by mainly by the IDEA collaboration for FCC-EE, that should feature this compensation of electron, but also hadron, for obtaining the excellent resolution necessary for separating the W and the Z hadronic decays. The RD4 photodetectors and PID, this is necessary also for the calorimeters because the optical calorimeters are read by photodetectors. The drivers here are the Illumia LSC, again, LSCB and LIS-free, and also future other colliders, and also the FCC experiments. So for the particle ID, we have the range imaging Cherenkov detectors. We will need, we will have high particle rates at Illumi, but also in future accelerators. So we need to resolve multiple and overlapping Cherenkov rings. We should have a great spatial and time resolution of these photodetectors with fine pixelations, and with a precision timing below 100 picoseconds to suppress the background. And again, the radiation harness, the materials and sensors must retain their properties under the radiation. A good example of this is the development of these solid state single photon detectors as devices for the LIS-free and FCC. That are based on a mix of gas and aerogel radiator and silicon photomultiplier modules. I said that the main challenge for the silicon photomultipliers is the dark current, dark noise, and also the crosstalk. So we should have in the future detectors, silicon photomultipliers with low dark count rates below 100 kilohertz per millimeter square. Okay. So I'm not going into details of the quantum and technologies. We have talked about it yesterday. Just to say that in the DRD5, they have several work packages where they are testing and studying novel materials, kinetic detectors, spin-based detectors, superconducting, optomechanical sensors. And here it looks at the major challenge is the scaling of these detectors from single channels to multi-channels. And as I've said before, the relevant topics for accelerator physics that are studied nowadays are the chromatic calorimetry and the superconducting nanowires. For the electronics, we have already huge opportunities with the modern technologies with a transmission speed of 100 gigabit per second with very high performance FPGAs. But as I said before, the complexity and the cost associated to their use also increase. So in the DRD7, they are studied solutions for this problem by considering several topics, the silicon photonics, the wireless data transmission, the intelligence on the front end, the high performance ADCs and TDCs, and also they are studying the properties of these devices in extreme environments, cryogenic or radiation, are the electronics. And it is nice that they are trying to develop a model for the development of these devices. What this is the scheme followed for the MEDIPIX TimePix chip at CERN, taught for the vertex tracking, but also for other scientific applications, biology, medicine, also industry. That includes also the collaboration with several partners, private and not. So yes, we are developing an efficient method for an efficient framework for developing this system. The DRD8, the last one, the mechanics and integration, another transversal collaboration. Basically, they are studying the materials for the structures, as an example of vertex detectors, also the cooling systems, but again, application for remote control with robots, as an example, and also the softwares, tools to connect engineering designs with the physics simulation. So this is a very broad collaboration with different topics that are useful for all the experiments. Okay, so I am at the end of the talk. So as you have seen, there is a very long list of R&D activities for detector technologies. As I told before, the next generation of detectors, LSB Upgrade 2, LS3, EPIC, they are approaching the TDR phase, so the technologies should be mature for these experiments in the next years. But the concepts for the detectors at the E+ E- colliders are already at a mature level, and the technologies developments for the E+ E- colliders detectors proceed at full pace. We have already convincing concepts for the muon collider detectors, and they are going through significant developments to be ready for having a muon collider in the 50s. And the technologies R&D is in synergy with the ILUMI and the E+ E- colliders. The FCC-HH detectors is the most challenging system ever taught, but we have time to develop it, and we will talk about it in the next talk. So the DRD collaborations have taken these challenges, and let's say they will bring us to the future of the high energy physics measurements. And that's all.
All right, thank you. What questions do you all have, or comments or thoughts?
Hi. Can you show again the slide, quite at the beginning where you showed the comparison between the muon collider and the HH development?
Well, it's not really a comparison, let's say. It's
it's
just general considerations.
Actually, quite small. The challenge is rather the so that you are like in a heavy ion type of environment, right? So you have lots of stuff from the beam-induced background, but the collision rate is small.
The collision rate is small, but with the simulation of the beam-induced background, we have seen that unfortunately the radiation levels are at these levels. Maybe there are differences between, I mean, it is not exactly the same. There are differences. Sometimes the radiation level is even more than the ILUMI IC in several subdetectors.
So which ones? Like the
like the calorimeters, because they have a huge flux of photons. But yes, unfortunately, this is the situation.
So it means you cannot use anything like crystals or things like this in
No, we can use crystals as an example. The Krillin. Now I don't have slides on Krillin, just a figure, but I can tell you more. As an example, this is a Cherenkov. This is proposed for the Muon Collider. These are crystals of the lead defluorite for the and so you have Cherenkov light measured by silicon photomultipliers, and these kind of crystals they have a sufficient radiation hardness for that environment. So yes, we can use crystals.
Okay. And then I have another one, if I can. I don't know if there is other questions on this. Again, on the table you showed before.
Ah, yes, okay.
You have to go all the way back
Okay,
again.
I go 20 slides.
So
Yes.
yes, this neutral hadron energy resolution, which is aspirational, seems very aspirational. I mean, I've never seen any hadron calorimeter that provides 20% of the square root.
Yeah,
of
probably the dual readout calorimeter of ID as an example can arrive closer, but I don't know. I have several doubts, and the environment is very different.
Yes.
By the way, aspirational means
I know.
Yeah, I mean the baseline is fine.
No, it's your aspirational photon energy resolution is not very ambitious. It's very actually this is achievable with almost any sampling calorimeter. But
Oh, yeah, you're right. I mean, yeah, we are fine with the baseline, but if you're able to provide some readout compensation for the Muon Collider, and we at least improve a bit of this, it will be better. But again, it's not mandatory. This is what means aspirational.
yeah.
Okay.
Just to add. We do super care about, say, WZA. Going to be a crucial thing. I don't know that we really have studied.
No, I haven't seen that study. This is more like a guess. It's true. This is necessary for having the W and Z separation.
Because
It's
also,
really difficult to achieve this also with the radiation level.
also because in that case, what matters is not so much at the end the neutral hadron energy resolution, but it's the jet energy resolution.
Exactly. So it should be considered the full peak.
Yeah, which is at the end maybe your single neutral hadron energy resolution is not that great, but if you have a good particle flow compliant calorimeter, you can
Yes,
compensate
exactly.
for it.
We can try to compensate with different ways.
But I mean, I guess at the end you want to do all Higgs physics also, so there you need a good hadron energy resolution. If you want to do Higgs to strange or anything like this.
I mean, let's say the
you need
baseline is the separation between X and WZ is fundamental for X physics. The background level of X and WZ is more or less the same.
But
I mean,
also for X to CC bar, you need a lot of
yes,
you need good
exactly.
energy resolution. I mean,
exactly. And then we should see which kind of physics we can do with this WZ separation. I mean, if this comes after the FCC-EE, I don't know which will be the measurements that can be.
But you have an order of magnitude more Higgses, right? So you would like.
Yeah, no, for the X,
to,
exactly. But for the X, I mean, this is perfectly fine.
Yeah, I mean, the more the better.
Yeah, of course.
You have large the rare channels. If you have large backgrounds, if you have 2 times better resolution, is square root of 2 improvement. I mean.
Yeah. Yes, it's true.
And sorry, yeah, I'm not sure exactly what went into the word boosted at the bottom there, but we've been talking about this past week or
Like it's only tracking. It doesn't look like it's tracking. It looks like we. Yeah. It's on TV, I'm young. Okay, excellent. Any other questions, comments, thoughts? Do you want to?
No.
Okay. Fantastic. Scariest part to you about reaching each of these detector performances?
The scariest part, I don't know. As an example, the development of these maps devices, or again, the development of devices with an extreme time performance that is needed even for the Lumia SC. I'm a bit scared on the fact that we will really be able to arrive to this. Where is it? No, maybe to the 30, let's say to the 30 picoseconds soon. Because this is not needed just by the idea, but also by the LCB X2 as an example. And I am in LCB, there is really a rush in trying to develop these devices. And so the next year, this is one part that scares me. Okay. For the FCC experiments, I mean, we have already mature concepts. I don't see really extreme challenges. If we are able to survive to Illumia LSC, probably the FCC detectors will be.
With 350.
Yeah, the drift chamber. Yes,
The chamber is not
the
as
drift
simple.
chamber is not so simple. They've shown that they think to have it under control, but let's see what will happen in the reality with respect to simulation. But we have time to develop it. Not so much time for FCC if it will start in 40 and something. But.
Right. Okay, let's move on and let's thank our speaker again. Lorenzo.
Thank you.
And